In my first video on this topic, I told you that total uncertainty in a quantity derived from experimental measurements is equal to the root sum square of bias and precision, where precision is typically determined using a student's t-distribution due to the small number of experimental samples taken at the same conditions. And bias is the root sum square of the weighted biases, and that the first step in determining bias is to write the derived quantity in terms of direct measurands. But that assumes that the derived quantity can be solved explicitly with respect to the measurands. What if that's not the case? Before I go further, let me state the thesis of this video, which is that if your derived quantity has an explicit solution, then do a bias analysis by taking the root sum square of the weighted biases. But if your derived quantity requires an iterative solution, then do a sensitivity analysis by taking the root sum square of the fractional change. Now, if you understood everything I just said, for heaven's sake, please stop watching. But if it sounds like I'm talking gibberish, grab some coffee and buckle up. First of all, what do I mean by an explicit solution? In the previous video, I determined density from the pressure and temperature measurements. I add a known quantity for everything on the right-hand side. So that's one equation with one unknown, which means the problem is fully defined. The unknown quantity only shows up once, alone, on the left-hand side of the equation. That's an explicit solution. Basically, it's the kind of equation you were taught about in high school algebra. And that algebra allows us to do the calculus. So step 2 is to determine the partial derivatives of the derived quantity with respect to the measurands, which are then plugged into the root sum square where they weight the biases. These derivatives can only be solved for an explicit algebraic equation. So let's look at a situation without an explicit solution. All my examples come from the laboratory that I run, which is a combustion shock tube. I'll spare you most of the details of the shock tube operation, but for this example you should know that I have a mixture of fuel and air in the driven section here. The driver section is used to send a shock wave into that fuel-air mixture, which compresses it down here into the test section, where all my measurements are made. If we zoom in on that test section and look inside, we see an incident shock wave pass through the mixture, achieving some level of instantaneous heating, which then reflects off the end wall and shock heats the mixture again. The value of this is that this fuel-air mixture has been heated to a very high temperature, usually 1000 Kelvin to 2000 Kelvin, and heated so fast that it has not had a chance to react. But it will react within a matter of microseconds, and I need to know the temperature of this gas, called T5, before it does. There's no physical probe in the world that can record a temperature of thousands of Kelvin over the course of microseconds, but I can calculate the temperature from other measurable shock properties. I use a series of pressure transducers near the test section to record passage of the incident shock via pressure spike. The time between spikes and the distance between transducers gives me a series of incident shock velocity readings, which typically decrease slightly as the shock compresses the reactants against the end wall. If I extrapolate a best fit line from those measurement locations to my test location, I get the incident shock velocity in the test section. I have plenty of time before shock initiation to read the initial conditions of the gas: temperature, pressure, and composition. Let's assume the gas composition here is stoichiometric ethylene and air, which is a mole fraction of 0.0654 ethylene, 0.1966 oxygen, and 0.738 nitrogen, which sums to unity. From these 6 measurands, I can determine both the temperature, T5, and the pressure, P5, in the gas behind the reflected shock, using the normal shock equations. This is the typical equation, reworked a bit from equation 2.37 in this textbook, for determining T5 from initial conditions and shock parameters. We'll call this equation 1, where gamma 5 is the specific heat ratio at state 5 conditions, and M1 is the Mach number of the incident shock evaluated at state 1 conditions. T1 is the temperature of state 1 before the incident shock passes through, and that's it. Just those 3 variables. But remember that step 1 in the bias analysis is to express the derived quantity in terms of direct measurands. Mach number and specific heat ratio are not direct measurands. They're not constants either. Here's our list of direct measurands again. Let's put that list down at the bottom here for reference. We need to find a way to write the equation for T5 in terms of these measurands. Let's do Mach number first. Mach number is the incident shock velocity divided by the speed of sound. But the speed of sound is not a constant. It depends on the composition of the gas, the specific heats, and the temperature. Replacing C with those parameters gets us a little closer. Now MW is the molecular weight of the gas mixture, which is the average of all the constituents. To get that average, we multiply the mole fractions, which are measurands, by the molecular weights, which are constants. So I suppose I should start a list of constants too, and add the universal gas constant to it, and we'll call this equation 2. But CP1 is the constant pressure specific heat at state 1, and that's not a constant or a measurand either. It can be determined using a temperature-dependent 5-coefficient polynomial developed by NASA. Although A1 through A5 are provided in a database from NASA and are therefore known, they do have an uncertainty associated with them. So we'll treat those as measurands. Now, note that I've written the equation for C sub P generically, but those 5 constants depend on the gas composition. So it's actually a summation, and there are 3 sets of those 5 coefficients, one set for each constituent in our mixture. So now just keep in mind that all of this must be substituted for CP1 in equation 2. I'll need the same formulation at state 5, and I'll call this my equation 3. Where equation 4 is gamma 5 expressed in terms of CP5. So at this point, I have 5 unknowns, and I have solved for each of them in 5 equations. The problem is fully defined and solvable. I have 5 times 3 equals 15 coefficients, plus 6 other measurands, which equals 21 total measurands. In order to write T5 in terms of direct measurands, I'd have to plug equations 2, 3, and 4 into equation 1, and then set about determining partial derivatives of that giant equation for T5 with respect to my 21 measurands. That is daunting, but possible. The problem is here. If I plug this into equation 4 and then that into equation 1, I'll have T5 on the left-hand side of equation 1, along with several instances of T5 on the right-hand side. I assure you, you will not be able to rearrange that to get T5 alone again on the left-hand side. So we have a fully defined solution for T5, but it's not an explicit solution, which means that I can't determine the partial derivatives, and my dream of completing history's most epic bias determination are dead. Or are they? Here's the solution. We simply make an initial educated guess for the value of CP5. Then we can plug that value into equation 4, 4 into 1, and 2 into 1, and solve for T5. That value is just our first best guess at T5, but it can be plugged back into equation 3 to give an updated value of CP5, and we can repeat or iterate the process several more times until the values of T5 and CP5 stop changing, which we call convergence. This is a complex and repetitive, but luckily for me, there is a well-established MATLAB code that automates this particular problem iteratively, solving for T5 and all of the thermodynamic properties of the gas behind both the incident and reflected shock in a shock tube. It's called the Frozen Chemistry Shock Solver, or FROSH for short. It was developed at Stanford in 2014, and I'm oversimplifying its solution method a bit for the purpose of this video. It's available for download here. It was first described in Appendix A of this thesis, and this is a more up-to-date reference for it. Let's see how it works. I plugged our example measurand values into FROSH and commanded MATLAB to output every iteration's values of CP5 and T5 until it gave me the final value. The first guess for CP5 is just the value of CP that FROSH determined behind the incident shock, referred to as CP2. This is the resulting T5, which, when applied to equation 3, gives a new value of CP5, and in turn, a new value for T5. This is just a wacky coincidence. As we continue through our iterations, we can see that the difference between each successive new set of values is getting progressively smaller, until the final two values for CP5 match to within 5 significant digits, and the temperatures match to within 7. This meets the criteria set in Frosch for convergence, so I'll report my T5 as 1299.6 Kelvin. Great, but I still don't know the bias on that reading, and I can't calculate partial derivatives from an iterative process, so what's the solution? The answer, finally, is a sensitivity analysis. This is the basic equation we'll use for this sensitivity analysis. Throughout this discussion, you'll notice that some of the vocabulary is different from a bias analysis, but the fundamental ideas remain the same. The first new piece of vocabulary is here, where the term bias is replaced with the variance. But this is still a root sum square, and now the weighted bias has been replaced with the fractional change in the derived quantity due to a perturbation in each input I, where the inputs are our measurands, and the perturbation in I is a change from its nominal value equal to the value of its bias. So there are many ways to perform a sensitivity analysis. I won't go into each one here, but the root sum square method that I'm currently describing is sometimes called the one factor at a time method or the most likely scenario method. It assumes that the input variables are independent or uncorrelated with each other, which will come up a little bit later. I've indicated that that's the method I've used by including this subscript on my variance term. So here, T5 is the value we just calculated, using these nominal values of our measurands, which was 1299 Kelvin. Each of these values have their own instrument bias, and these biases define our perturbations. And delta T5 is the change in T5 that results if we recalculate it after perturbing each measurand up or down by its instrument bias. In our case, we had 21 measurands, but we can simplify that list a bit down for simplicity to this list. You can see I've taken some liberties with my determination of what inputs must be considered individually. T1, P1, and UIS, or incident shock velocity, are straightforward, and I'll treat those exactly as the math says I should. However, I've grouped all my NASA coefficients with a single uncertainty. This is not technically correct. There are methods available specifically for determining the uncertainty associated with polynomial fit coefficients like these. However, those methods require some information about the fit determination that I don't have. They're mathematically pretty rigorous, particularly for fits with large number of coefficients, and I'd have to repeat that process 3 times. I'd likely get a result pretty similar to the conservative estimate of the fit's uncertainty that I've shown here, which is already pretty low. Remember, uncertainty analysis is not some purely theoretical mathematical exercise. It's an engineering tool from which real-life decisions are made. As we'll see in a few slides, these coefficients are not what's driving my uncertainty. So going down a rabbit hole on these coefficients just to get the math exactly right is a waste of time. Finally, I've only considered my ethylene mole fraction. Recall that the mole fraction must sum to 1. So if I perturb ethylene, I have to perturb the other two to maintain unity, which means these 3 values are correlated. I can pretty easily continue with my chosen sensitivity analysis method and account for this correlation at the same time. I'll assume that nitrogen and oxygen mole fractions change proportionally in the opposite direction from the ethylene and determine the fractional change in T5 for only that situation. Technically, I should repeat the process for all 3 species, but again, I expect the effect of my uncertainty to be negligible, so let's move on. So now, if we return to our variance equation, we're considering the fractional change due to those 5 inputs from my table. So n equals 5. And we can express this more specifically in terms of those 5 inputs. From a practical perspective, that means we'll have to run Frosch 5 more times. Once, where we calculate T5 using T1 equals 231.45 K, which is a 2 Kelvin perturbation above the measured value. Once again, where we calculate using P1 equals 573.98 pascals, which is 0.12% perturbation above the measured value. Once where UIS is perturbed 1.5% higher, once where the NASA coefficients are perturbed, and once where the ethylene mole fraction is perturbed. The results of such a sensitivity analysis are often presented in a plot like this, where the change in T5 due to the perturbations in each of our 5 variables is shown as either a negative percentage change or a positive percentage change. The lengths of the bars make it pretty obvious what the driving factors are in our uncertainty, which in our case is the measurement of the incident shock velocity. But remember, this is just the sensitivity analysis for temperature, and it only shows the individual input contributions, not the total uncertainty. If I wanted to know the total uncertainty, I'd need to repeat this experimental condition a few more times to get precision, and then I'd use a slightly modified version of the total uncertainty equation, where I've replaced the bias with the variance from the sensitivity analysis. And then I'll present the results in the same way I presented my standard uncertainty analysis in my other video. This table shows that the variance in T5 is primarily driven by uncertainty in the incident shock velocity. Total uncertainty is driven slightly more by precision than by variance. This analysis told us that we needed to improve our repeatability first. We did that by moving to something called double diaphragm operation, which gives us more direct control over the shock strength and therefore tighter control of T5. With our precision reduced, our primary driver became uncertainty in the incident shock velocity, which we should be able to reduce by adding a 5th measurement closer to our end wall. Stay tuned for those results. And now we see that even though I've completed a non-standard uncertainty analysis, the core utility of the exercise remains the same. The analysis led to 2 physical changes in our real-world experiments, so this was a practical exercise, and my backward-looking criteria is met. Another researcher could safely apply this uncertainty and estimate to their own calculations, so the forward-looking criteria is met. Finally, I didn't waste my time nitpicking input details such as the NASA coefficients and mole fractions that would not have improved the accuracy of my results enough to change any of my decisions. I hope this was helpful.